This lecture is going to introduce something that just another organizational tool for these types of problems here that seem like they have a limited number of probabilities given, but in reality they've got more than we think, right? And it's not a Venn diagram problem, but it's going to be one that is just a different organizational tool. And it's going to be a tree diagram, and it's going to kind of look like a family tree, just kind of tipped up 90 degrees. So it's not going to be what you necessarily maybe think of when you think of a family tree, where you've got mom and dad, and then the kids branch off, and so on and so forth. Right? It's going to be up on its side. So I'll summarize the context here. There is a lot of context in this problem, and basically what they're saying is if you have a sobriety checkpoint and you get stopped, they're telling us that 80% of the time a trained officer can make the right decision as to what to do with the driver. That's one probability that we have. Then the other probability that we have is that they're operating this checkpoint at a time when they suspect 12% of drivers have been drinking. So there's actually a lot there. There's actually a lot going on that we want to organize, and we're going to use the tree diagram to do that. So we're going to start with that first branch. So always working in context, and I want skinny ink here. So our first branch, the first decision, not decision so much, but the first event that happens is the driver comes up to the checkpoint, and they either have been drinking or they have not been drinking. The probability that they have been drinking is 0.12 as given in the problem. So 12% of people are drinking when they pull up to these checkpoints. That means 88% have not been. Right? Pretty straightforward. You're going to be one of two groups. Imagine you get there and you say, okay, you've been drinking or you've been not drinking. So now we have let's go up this first path, the first branch, and we've got two others. This is where we work in that 80%. Well, 80% they do the right thing. Always work in context, right? Always work in context. If they have been drinking, if the driver has been drinking 80% of the time, what will the officer do? They will detain. Meaning 20% of the time, they will release. I'll just put that with an R. So we're not, it's that make the right decision, which is a little vague here until you look at it in context. That's why don't just look at the numbers, look at the whole problem, because otherwise you won't be able to figure this out. We go down below. And 8% of the time, if they have been drinking, if they haven't been drinking, rather, 80% of the time, they will release. And 20% of the time, they'll get it wrong and detain people that haven't been drinking. Now, from here, we can find these probabilities. We can find 4 different probabilities. These are really the only 4 outcomes you could have. You could have drinking and detain. Drinking and detain. So we multiply these two, 0.12 times 0.18, that's 0.096. You could be drinking and released. I hope that doesn't happen too often. Drinking and released, and that's 0.024. And we're just using the multiplication rule here. We're going down the branches, right? This is the best outcome right here, not drinking and released. Right? That's what should happen. You shouldn't be drinking, and you should be released as a result. Right? And that's 0.704. Yes, I did these before. And then the probability of not having had anything to drink, but being detained anyway, right, is 0.176. Not been but detained. All right. So now we've got all these. Now we've got all these probabilities. So now let's look at the actual questions. Part A. You are stopped at a checkpoint and, of course, have not been drinking. What's the probability that you are detained for further testing? Okay. Well, this one we don't have to go into these because we're not talking about this and this. It is a conditional probability. We are looking for the probability of being detained given that you weren't drinking. Looking at this with a tree diagram, what's the probability that we are detained if you haven't been drinking? It's as easy as saying 0.2, right? That's this number right over here. I don't want to circle. I don't want to get too much stuff in here, but well, I can actually. It's right here because that is the probability that you were in that group, the good group, but somehow you got detained for further testing. What is the probability that any given driver will be detained? We don't care we do really, but for this question, we don't care whether they've been drinking or not. We're just trying to find what's the likelihood that you get detained at the sobriety stop. So you could be detained after you have been drinking, which is this one up here, right? And 0.096. Actually, I'm going to move this down here for just a second. Hold on. Actually, I can fit it up there. I can fit it right where I had it. Okay. So the probability that they were detained after their drinking was 0.096. 0.096, or they were detained after they had not been drinking, which is 0.176, for a total of 0.7272. So part C. Part C. What's the probability that a driver who is detained, that's a condition, we know they're being detained, right, has actually been drinking? So drinking given detained. I'll write detained out here. Right? So it's a conditional probability. So the numerator is the probability that they were drinking and detained. Right? The probability that they're drinking and detained. So that's going to be our 0.096. Right? 0.096. And then the probability that they were detained, period, which is very nice of the author to have us do that in the previous problem. And that gives us a probability of approximately 0.353. So if you've been detained, there's a 0.353 probability that they've actually been drinking. And then the other, again, this is just practice. What's the probability that a driver who was released had actually been drinking? Again, we're looking for the probability that someone was drinking if we knew they were released. So we find the probability of both these events occurring, drinking and released. Drinking and released is right here, 0.024. And that's a 4. That's a 4. It's not making it any better. And then released, we do have to take into account, we don't have this yet. We take into account the 0.024 because that's one of the situations where you're released. And then the other one is the 0.704. Right? And we calculate that out. And it's about 0.033. So about, if you were to poll the people that were released, if you were to kind of do a check on how well the cops are doing their job, if you took all the people that were released and 2 miles down the road, you took them, you had them take another breathalyzer test, only 3% of them would actually have been drinking, right? So a tree diagram combines a lot of different things, especially with the types of questions they get to ask with them. They combine the multiplication rule, they combine conditional probabilities, and they incorporate the addition rule as well with these types of questions. Right? Please let me know if you have any questions about this. This lecture was a little bit longer because we didn't really get a ton of time to do this in class, but this will definitely be on the summative. So let me know if you have any questions. Hope this helped.